everywhere where we are running around, we are faced with this question. What have you done today to protect the climate? So, and I can only say, again, impressed from Norway, how many people in the meantime have switched over from the fuel cars to the electric cars, so they can all tell, I have done something for the climate. Yeah. So others who have not switched over, they have to tremble and to scissor. My answer to this is I tried to understand in recent years a bit better climate and the effects, and to do research for truth. That is my answer to this question. So far, let's look to the outline and what I try. When we look to this headline, I think it is good first to have a look back to the climate of the past and also some native impacts to understand what's going on and what is discussed about climate nowadays. So then I will briefly touch the explanation of the interpretation and the interpretation of the IPCC. What are their explanations for the climate change? And I have to face this with some own calculations and considerations, particularly concerning the carbon cycle. So when I hope there is still some time further on, I would even like to briefly touch the question how far CO2 as a greenhouse gas is also impacting and participating to global warming. And one of these drivers, natural drivers, will be the solar radiative forcing. So far the outline, and let us have a look to the climate of the past for the very first, the longest period, of course, of 4 billion years. We have no real information about this. But since the Cambrian, 550 million years ago, which is also an extremely long period, from some proxies we have some first ideas. And you see here that we had temperatures which are scaling here in this way, which were about 10 degrees higher than nowadays. Yeah, and let's see this on this scale. Temperatures varied over more than 10 degrees over this period, almost 10 degrees even higher than nowadays. We are here at this position, at this point, and over the 4/5 of this whole 570 years, you see here indicated by these red areas, we had warm ages, and only 1/5 of this whole period there were ice ages. Now, an ice age is defined when both pole caps, or even only one cap, is covered with ice. So the consequence is we are living in an ice age, the Quaternary. Many people don't realize that we are really living in an ice age. Yeah. So it is really crazy to ask when we are discussing about half or 1 degree more, that we already would reach a tipping point which could destroy our further living and our further future in this way. So also we see this green graph now here, which represents the CO2 over this period. As far as possible from this proxy data, this is possible. So, and this scale shows you this is even very conservative. 6,000 ppm, this means so much as 6 parts per million, 6,000 parts per million, or 6, yeah, so 0.6% in this way. This is 15 times the concentration we have nowadays. 15 times of this concentration. And this scale, when we look compared to the red graph here for the temperature, there is no real correlation between temperatures and the CO2 concentration. So we are even living here in an absolute minimum of the CO2 concentration, which is necessary for photosynthesis and for survival of our life. Now, what brought about these changes? What were responsible for these changes? And let's look here a few animations and graphs going back to history, known as Milankovitch cycles, where the Earth is discussed and considered as a gyro with different degrees of freedom compared, rotating compared to the orbit of the Earth around. So, and first, what we see that the Earth's axis of this gyro is not stable all the time, not only rotating in this way, but also this axis itself is slightly oscillating back and forth over periods of 41,000 years. So additionally, we have the whole rotation of the Earth around the Sun, which is known as the perihelion rotation, with 112,000 years. Yeah, and all together, this gives a modulation of between 19 and 24,000 years. On the other hand, we have the ellipse. The curve, the Earth rotating around the Sun, and what we see here, when this ellipse is changing, is also changing over about 100,000 years, and due to the intensity dependence to the distance to the Sun, which is scaling by the square. Yeah, this means we have relatively strong changes, intensity changes between 2 and 23% of the incident radiation of the Sun. So, and when this Earth is rotating here on its orbit, so we have a situation. Look to the arrow here, and when we look here in this position, the gyro has just the opposite position 20,000 years later. So that means the distance here between Sun and the Earth is once in this position bad for the southern hemisphere, and in the other position it is bad for the northern hemisphere. So this also gives an additional impact, and so we see with up to 28%. So this additionally is overlaying with some oscillation of the Sun around the barycenter, the mass of the whole solar system, also modulating the distance, the eccentricity of this trace. So altogether, this gives a lot of variations which depend on the special constellation of the Earth to the Sun. This only to have in mind for the future remarks I will make. So let's look with higher resolution to the last 4,000 years here from ice cores reconstruction of the temperature in Greenland relative to the annual local temperature. We see real periods of warmer periods and very rapidly decreasing, and with periods of about 300 to 600 years. So also here is the temperature difference from here to the actual temperature between 2 and 3 degrees that it was in previous times warmer. See, 4,000 years ago, we call this the Holocene, or the interglacial of our actual ice age. Yeah. So, and the curve here, or the decay, can be explained by the Milankovitch cycles, but these fast decays here, we have this and back and forth oscillations. This is only one trigger. Could be the special circulations we have in our oceans, particularly here shown the global conveyor belt, or thermohaline circulation, as we call this. And the dominant parts of this are found here for the, let's see here, for the Atlantic meridional overturning circulation and the Southern Ocean overturning circulation. And as subsystems of the AMOC and the SOC, we have, for example, here particularly strong influence to Norway, here to the northern countries, by the Atlantic multidecadal oscillation, and for the Pacific, the Pacific decadal oscillation. These are coming up more or less periodically between 50, 60 years and up to 200 years. On the other hand, we know this phenomenon of El Niño southern oscillations, which have another origin and which are coming up with an unregular period, with an unregular behavior within 2 to 7 years. So here we see a plot from this AMO with warmer and colder periods in this way. And I would like to point to your attention to this area here around 1940, where we had a relatively warm period before it was cooling again. So this correlates, as we will see, acceptable quite well with temperature measurements. Now, next to these currents, oceanic currents and impacts, we also have some solar activity which can modulate and impact the cosmic radiation coming from galaxies, from the outside. So here you see, for example, this is a graph from Hendrik Svensmark. I will show this afterwards. And there we see, for example, here the so-called sunspot number which is observed already since Galilee. Yeah, and there was always the question if these spots we can measure with a telescope on the surface of the sun, if this is an indication of a higher or lower activity of the sun, and with an increasing radiation. So, dominant here in these oscillations, you see a period of 11 years known as the Schwabe cycle. As the understanding is the background, we know that this is connected with the switching back and forth between two positions of the solar magnetic field. And so this magnetic field on its own has an impact on the generation. First of all, it has an impact on the cosmic ray. So when we have higher activity of the sun, then obviously the cosmic ray is reduced. It is in some way dependent. In this way, what we see with a high correlation, when we have maximum activity, we have low cosmic ray intensity. And the cosmic rays are the nucleus for generation of small droplets for condensation of water vapor and to form respective clouds. So when we have a higher activity of the sun, we have lower cloud formation, which means that the higher intensity of the sun, which comes to the Earth's surface, is even amplified due to a lower cloudiness. So, and this is measured, as you see here, the cosmic ray, this brown graph, and the lower cloud cover here as a blue graph. They are very well and highly correlating to each other. So, and this model and this interpretation goes back to Henrik Svensmark, and we can expect even, we call this the solar-induced cloud feedback, which can even give an amplification by a factor of 3 to 5 of the variations of the cloud, which is only about 1 per mil and not more. Now, let's look now to the measurement of the temperature. Here, a reconstruction of rural, 30% rural and 70% oceanic surface temperatures. And there we see again this strong maximum around 1940 with the decay, and afterwards a stronger increase up to the actual situation. But there is obviously no correlation to the CO2 concentration, which is shown here as the green graph. Yeah, so we need a better explanation than only increasing CO2 for our temperature increase. I want to explain and what this really means, these temperature measurements. So wide field solar measurements are available since 1978. And in average, we can find, particularly for this period, for this steeper increase here, we find values of about 0.13 centigrades per decade over 10 years. 0.1 degree over 10 years, which means 100th degree per year. This we should compare to temperatures we find on our planet, yeah, between different zones climatic zones. Here, for the Topan Basin in China, there were measured temperatures of plus 82 degrees, and in the Antarctica, we have a new record, not so old, of almost minus 100 centigrade. So this means more than 180 degrees difference. It is even one location in Siberia where are measured temperatures at the same location over the seasons from wintertime to summertime of more than 100 degrees. So, and there comes up the question, we are talking about 1/10,000th of temperature differences on Earth over 1 year, 1/10,000th over the natural variations of our Earth. Yeah, so which will be measured and specialized as a strong perturbation of our future life. Yeah, and on the other hand, year-to-year variations. When we look to these measurements from year to year, this is about with an uncertainty of 2 centigrades from year to year. And again, comparing this with this 100th degree per year, this is 200 times larger variation and error for temperature measurements from 1 year to the year than what we can measure as a long time increase of the temperature. Now, only to make clear what is the situation and what we could and what we can learn from the past, from history, or climate history. So, with the inception of the industrial area for many climate scientists, particularly from people from the IPCC, national impacts no longer exist. They claim only fossil fuel emissions are responsible for the increasing CO2 concentration in the atmosphere. So, also, almost all of the temperature increase is caused by this greenhouse gas. This we hear every day, and we see this in our news, in the TV and broadcasting and everywhere else. So let's look a little bit closer to this interpretation of the IPCC. What is the background that they can claim in this way? Now, first of all, we see before 1850, so this almost beginning of the industrial area, the carbon cycle is assumed to have been and to be in balance, yeah, with an atmospheric CO2 concentration of 280 ppm. So the emissions and absorption as a cycle, nevertheless, is existing with about 80 ppm per year. This means, in average, the CO2 stays in the atmosphere for 3.5 years, about this. Now, and this is assumed to be absorbed and re-emitted. But in reality, this model only discusses this is circulating, overturning, and not really absorbed in this way. Over the industrial area, we see emissions due to the fossil fuel emissions were increasing, and the circulation, the emission was increasing by 26 ppm per year in the meantime. Now, this means at the moment, we have human emissions of 4.8% of the total emissions. I mentioned before, this means the 80 plus 26 means 106 ppm per year. 4.8% of this are human emissions, which go back to calculations by the CDIAC. This is the Carbon Dioxide Information and Analyzing Center, who are counting all emissions all over the world. So, and this is an emission rate here, as we see, of 5.1 ppm per year. Now, from these emissions, 2.5%, so that means from this 4.8, or a little bit more than half, 45% are directly absorbed. That is the interpretation of the IPCC, are directly absorbed. And the other part, the 46%, this is called the airborne fraction. This is emitted and stays in the atmosphere almost forever. Almost forever. This means the CO2 increases from 280 to 410, which is, at the moment, we even have 420, but this is an average over the last 10 years, as we find from the excess reports of the IPCC. And what is emitted and stays as airborne fraction will stay there for more than 100,000 years. This is the idea. So this is called an adaptation time. On the other hand, we have this overturning and rotation, or the residence time, we call this better, which means when we have this concentration of 410 and divide this by the emission rate, the 106 ppm per year, we come to an average overturning time, residence time of 3.8 years. So now this sketch shows it again on another basis, what I was just discussing. We have here the oceans and land, the surface, and here the atmosphere. And look, the additional emissions of 130%, they will stay here for more than 100,000 years in the atmosphere. On the other hand, this injected fossil fuel emission rate here is oscillating back and forth within an additional part of 26 ppm all the time. At the same time, when this is here all the time oscillating back and forth, we see that new injections here to the atmosphere are splitting one part here as the airborne fraction, the 46% herefrom, and the other is directly absorbed. So this is very strange to understand that here is, from previous times, there was injected fossil fuel, and this stays in the atmosphere forever, and new emissions are to almost one half are directly absorbed. So the balance, the mathematics and the mathematicians and the physicists, they like equations to explain what they try themselves to understand. So the change in the concentration change, delta C of CO2 over the time, here, for example, over 1 year, delta T equals 1 year, gives this emission here to the atmosphere and is reduced by the absorbed part, 1 minus AF times EF. So when you calculate this, this is nothing else than the increase here of the concentration in the atmosphere. And when we plot this we get this here, the sawtooth curve here. This is from the Mauna Loa measurements with the seasonal oscillations, and looking to this model, this simple model, this is plotted here as a red graph. This fits almost exactly. This is a strong argument that this model could be real and it could be really present the actual situation. So the airborne fraction here shown as a green graph with almost 46% fits well in this picture. But let's look to this, what I have tried to describe. There are indeed some real basic problems with this, and similar carbon models, not only this airborne fraction model, also more complicated models have some similar problems. Here only a representative for this airborne fraction model. The constant, they were assuming a constant natural cycle of 280 ppm, and they neglect all additional native emissions. Okay. This contradicts paleoclimatic and actual observations. We have many indications that there all the time we have natural emissions, and not only the fossil fuel emissions. I come back to this later. 55% absorption of new emission, but no uptake of previous emission. I made clear this point beforehand. This is a violation of the equivalence principle, one of the very basic physical principles. This cannot be understood in this way. Then we have absorption. The absorption is assumed to be proportional to the emission, not to the concentration in the atmosphere. When we look to all our natural systems, they are almost everywhere responding to actual concentration or to an actual perturbation. For example, a radioactive decay, the number of decay processes per time. So they depend on the actual number of radioactive molecules or the concentration. Yeah. So, and not to the injection, proportional to the injection. So this is at least descent to native decay process. The total CO2 concentration in the atmosphere is exchanged within about 4 years like an inert gas. Everywhere where we are looking around here in the environment of Oslo, the trees, they are living from absorbing by photosynthesis and absorbing CO2. Yeah, part of this can be by respiration can be emitted, but much later, and so we have a real absorption and not only a circulation process, and we have a real absorption and also real emissions. So the more elaborate burn model, some of you who are more familiar with these cycles, they are using even 5 different absorption channels and all proportional to the emission and not to the actual concentration. So, and this is also a real fault of these models. So we have to look for another, more consistent approach. To that, what I tried to explain, where we have some deficits in understanding or even hurting physical laws. So we tried to make an approach with real emission and absorption processes in agreement with all observations, I can say, and all physical causalities. These further investigations were done together with Murray, the late Murray Selby from Macquarie University in Sydney. He was one of the, I would like to remind to this, he was one of the internationally most renowned scientists in atmospheric physics, and already more than 10 years before this was discussed by different groups and people, even with the IPCC, his considerations and calculations raised significant doubts about the IPCC's explanation. But his ideas and ansatz, we say, were not in agreement with the understanding of his colleagues in Sydney, and so he was released, like Peter Reed and other people we know in the meantime. Who is not conformed on the party line with the IPCC, he is fired. Our approach includes temperature-dependent natural emissions, EN, I call this, as temperature-dependent natural emissions, and we have anthropogenic emissions, of course, what is only discussed by the IPCC. So this is the additional term here over the industrial area. So we assume this is the only assumption in this case. Yeah, we assume an absorption rate which is proportional to the CO2 concentration, in agreement with all these observations I mentioned. So in the atmosphere, and this is characterized by an effective absorption time, we call this tau effective. So this gives the absorption rate, the CO2 concentration divided by the effective absorption time. Together, this gives, as already discussed beforehand, for the airborne fraction model, when we look to the same symbols here, the change of the CO2 concentration per year depends what we are emitting. When you have a glass of water and you are filling this, yeah, this increase depends how quickly you are pouring in the water. So this is the emission we see here, En plus Ea, natural and anthropogenic emissions. And what is absorbed when we have a hole in the bottom of the glass or in some buck, then this is the losing term. So in our case, the absorption by the environment, by the adjacent reservoirs. This is called the balance equation for CO2 for the atmosphere, or the conservation law for CO2 in the atmosphere. A very basic calculation. And all further calculations and considerations are based on this more or less simple equation. So, one good indicator for this absorption process I was talking about, proportional to the concentration, is a radiocarbon as a tracer for the carbon cycle. This is almost ideal tracer, having the same behavior as the other isotopologues, only that C14 has 1 neutron more in the nucleus, but almost the chemical behavior and all the other processes are almost identical. So what we see is this C14 is naturally produced in the upper atmosphere, in the stratosphere. As you see here, neutron, this is the cosmic ray coming to the outer surface of the Earth. And so it has a collision with a nitrogen 14 atom. So, and it kicks out a proton I can repeat this. You see what goes on. The neutron collides with the N14, changes to C14, and the proton disappears. And in this way, this is rapidly oxidized by in the upper atmosphere in this way. So we have this natural production in the upper atmosphere, in the stratosphere, we call, so above more than 20,000 kilometers height, only with a concentration of about 10 to the minus 10%, so 10 to the minus 12, very, very small. But this radioactivity is very good. This can very sensitively be measured. And otherwise, the same behavior as the other isotopologues with the other, as you see, with C12 and C13. So the radioactive lifetime is more than the half-time, or almost 6,000 years, or the E-folding time, we name this, that this is decaying to 1 over E. E is number 2.7. So as for this natural decay processes, is this even more than 8,000 years, much larger than we are interested in any observations. So we have this as the background. But what happened in previous times, due to the nuclear bomb tests up to 1963, before there was made a stop of this first bomb test, the concentration was doubled due to a higher neutron concentration in the stratosphere, almost doubled to the natural rate. And this gives an ideal way to observe the further decay over the further time. And with the stop of this nuclear bomb test, we can check, we can control, is this a real exponential decay, as expected, what we expect when we are assuming an absorption or sequestration of some gas proportional to the actual concentration in the atmosphere. And so from this simple, again, balance equation or conservation law, in this case for C14, this results in such a mathematically in such an exponential decay. And here is a measurement which was taken in Switzerland on the mountain at Verbund. And you see this with some perturbation, okay, but in all together, this looks like an exponential decay. So this supports this ansatz. And on the other side, we have over the very first 4 to 6 years, we have these stronger oscillations here. So exponential decay and these faster oscillations, which can be explained by the Brewer-Dobson circulation, injecting particularly in boreal winters on the northern atmosphere, from the gases of the stratosphere into the troposphere. So, and this can be understood as these oscillations, which are seen from in this way. When we want to classify and to describe this more precisely, and this is very important for the further understanding, so, but I have to look to the time. Oh, yeah. So I have to hurry. Then we use a 3-volume system consisting of the stratosphere, the troposphere, or where we are living in the troposphere, and the surface layer, consisting of land and oceans. So when we have an injection with the mass fraction delta m in this way from C14 molecules, from the stratosphere to the troposphere, this reduces here the concentration in the stratosphere. This I have written here, the concentration as the ratio, the mixing ratio. This is nothing else than the mixing ratio of this mass amount compared to the total mass in the stratosphere. For the troposphere, this is not the same increase what we have as a decrease here, since the mass in the troposphere is about 10 times larger than in the stratosphere. The result is that we have a strong injection which gives a relatively small increase in the concentration in the troposphere. A similar situation we find between the troposphere and the surface layer, which also collects much more CO2 than in the troposphere. So altogether, when we solve this system, this three-volume system with these differential equations, then we get such a simulation. This is, therefore, I try to explain this gray line. This is the concentration, the first much higher concentration of the CO2 in the stratosphere. And most important, what we can compare directly with the measurements at Vermont is this blue curve, which represents the result for the troposphere. And we see this works quite well here with these oscillations, which can be observed with an absorption time, and now it is important, with an absorption time which can be as short as 1 to 2 years. While the IPCC is talking about at least several hundred years, but a rest even staying in the atmosphere up to 100,000 years. So we have direct absorptions, and which can be observed everywhere in the nature, which are rapidly, which are going very fast. And but this increasing concentration comes into balance with the final absorber, that is the surface layer. What is absorbed by the oceans, and what is absorbed by the plants, by the biosphere. So, and we see we have this fast oscillation, the direct absorption, and then slowing absorption with almost an exponential decay of 8 years. This can be expressed, I jump over, by a balance equation for all three volumes, and this has to be solved, and then we get this effective absorption times. So, but we won't go into these details. Also, an important point is still to look to these concentrations here, stratosphere, troposphere, and the surface layer over time. When we use this three-volume calculation I presented for C14, for the radioactive carbon, now use this in the same way for anthropogenic emissions. Anthropogenic emissions different to the injection of C14 into the troposphere is here, not from here to here, but that this is the anthropogenic emissions are directly injected to the troposphere. And looking closer to the solution of this three-volume system, we see this has the result that we get a magnified disequilibrium in the surface, to the surface, which you see that the red graph representing the surface compared to the blue graph, the troposphere, is in their distance is further increasing. So the population difference, the concentration difference is increasing. And when this is increasing, the re-emission from the surface to the troposphere is less possible, is reduced. So this process even speeds up the further absorption, so that compared to the C14 considerations, for the anthropogenic emissions, we can even expect slightly faster absorption, down to about 1 year as effective absorption time. The result is, when we look here at 2023, not so long ago, we find from this calculations that we get a concentration here of only 13 ppm. That is the contribution of the anthropogenic emissions compared to the natural emissions, which make the rest of this nowadays 410, but from over the industrial area, from 280 to 420, so compared to this 140 ppm increase. Yeah, this is calculated. This depends on the ratio of the mass ratio we have here to here. Sorry, not from there, from here to the surface, which is calculated with the ratio of 1/4. That means that the concentration here is in the surface area is 4 times larger than in the troposphere. When we consider even a larger layer, about 100 meters depth, ocean depth, with this increasing volume, also the concentration, not the concentration, the mass amount of CO2 in this larger layer, before it is sequestrated into the deep ocean, can even be 1 to 10. Yeah. Then also this concentration here reduces, and we find only 7.3 ppm with an effective absorption time of 1 year, which means we have in a contribution of only 5%. This was here still 9%, only about 5% increase over the industrial area as a perturbation caused by the emissions of fossil fuels. We can discuss how far is this real to calculate with one here 1/4 or 1/10. Yeah, we have not very accurate numbers, only some rough estimates. But the order of magnitude you see already. This is much faster than what is ever described by the IPCC. So how do we explain the much larger increase of CO2 over the recent decades? When we only have this small contribution, but we measure an increase of 140 ppm over 800, over more than 160 years about this. What is this? From where is this natural CO2 coming? These native emissions. So, what we know is that surface process, like emission and absorption, these are surface processes, and not only circulation, but real absorption and emission are depending intrinsically upon the temperature. This we see in the seasonal modulations, and only here a number, the seasonal modulations we saw on this graph beforehand, on this Mauna Loa curve. They are 6 times larger than what we have at the moment as fossil fuel emissions, which is 4.8%. So this is much larger, which can directly be absorbed. And also the absorption, again, the emission and the absorption. This makes the modulation we see there. So we have soil respiration even increasing exponentially with temperature, particularly in the tropics, not in the mid latitudes and higher latitudes, but particularly stronger emissions in the tropics. And we have also emissions and uptake by the oceans, but not so strong as in the tropic areas over land. These are main contributions. So we have to discuss and include in our further considerations this bioatmosphere, the biosphere, the oceans, and also permafrost. Yeah, this is also melting and emitting. And what is also often skipped and not considered, we have about 1 million submarine volcanoes. 1 million submarine volcanoes. And it is expected that thousands of them are active. Even there is a model that this activity is the initiator for the El Nino. We have more or less in this periods of 2 to 7 years. So we look to this curve again, the measured concentration at Mauna Loa as a reference standard for these calculations and for the CO2 concentration in the atmosphere. And we see these obvious seasonal modulations, which are over the years from here to here, not strongly varying in their amplitudes. They are almost the same. Therefore, there is a question, which is the additional source for emissions? We look to the derivative, mathematically derivative, so the difference you measure per time interval as a change on a higher scale, the concentration change to a time interval, yeah, more precisely. And this for a deseasonalized concentration. This means that we subtract these oscillations, these seasonal oscillations, but look more carefully to what is left, what can be seen behind these oscillations. This is nothing else than, again, the conservation law. Now we come to this conservation law in this way, and this we make the opposite, not the integration, summing up, but now the difference between different time points, so as differentiation. And we call this the net emission, consisting of the natural emissions, the anthropogenic emissions, and the absorption. Yeah, this prime means only that we are considering now without these seasonal modulations, which are perturbing the further interpretation, only the plots I want to show. Now, this net emission here, this is when we look more carefully to the Mauna Loa curve, yeah, as this derivative. And we see this is climbing up here over the years, not dramatically, but we see this increase, mostly representative for the, as I mentioned, for the tropical areas. And we see these typical spikes here, and here. And when we look more carefully to other data, we see this coincides quite well with the El Nino periods and oscillation or or events, so better events. So now, and this average increase here is only 0.03 ppm per year. This is less than 1% of the anthropogenic emissions. You remember this number here, 4.8 ppm per year at the moment. This is less than 1%, yeah? But this can be explained due to this fast absorption time. This is the reason that it is not climbing up and summing up so much, since all the time what is emitted, part is absorbed and reduces it to get again into a new balance. So, but this by no means coincides or gives any relation to the airborne fraction of 46% I mentioned beforehand. So, having this in mind, what I just showed you, we look now to the temperature, particularly in the tropical areas. In other areas, we have almost no real systematic temperature increase. Particularly the greatest increase in the tropics. So over this area in the tropics, we see a continuous increase over land and sea, which can well be here represented. We can look to satellite data, but the satellite data were only available since 1978. Therefore, we are using here the head SST, this is the sea surface temperature data from the headquarters center in London, or in Great Britain. So, and we see spikes here again, and when we look carefully, these are again the spikes we saw for the net emission I showed beforehand. So there is obvious a coincidence between this emission behaviors, these temperature events, and emission events. So this is a good reason to explain these observations by an increasing temperature. And so we go back to this net emission, that is the measured, the differentiation of the measured Mauna Loa curve, and we compare this with the calculation, particularly for the emission in, I mentioned this several times, in tropical areas, where we have almost a 10 times higher temperature sensitivity than for the oceans, the emission by oceans. And you see, when we compare this with each other, with such a calculation, this fits not exactly. This is so completely different data from temperature. And on the other hand, miles away, thousands of miles away to Mauna Loa, to Hawaii, yeah. But the main events and also this average increase fits very well between the net emissions and the temperatures. So, what we can do as last step, we can integrate this calculated red curve and compare this with the original measurements at Mauna Loa. So, and what we see here, first of all, this is very important as a note, we have emission in phase with the temperature here. We have a concentration. This concentration has a phase delay compared to the temperature and the emission of 90 degrees. And this is a very well-known result by Ole Humnum and Jan-Erik Solheim, and who was else doing Georg Sterdal, yeah? So, who were doing this analysis several years ago and indicating that that in this case, CO2 cannot be the driver for the temperature increase, since CO2 first is with a phase delay of 90 degrees, cannot be the origin or the driver for the temperature. So only opposite. Temperature is synchronous with the emission rates, and when you have this emission, this builds up the actual CO2 concentration. At least for these calculations, so CO2 cannot be the reason for the temperature increase. So, and I will come to an end, jumping over some other discussion, but coming here to this final results. When we are comparing this with this calculation with the measurement, then this means the calculated net emission, temperature-dependent net emission. This was this red graph I showed last. So this is the net emission additional to the anthropogenic emissions, and then we have to include the seasonal oscillations on top, which we subtracted beforehand. So what we get as calculation, this magenta curve here, which fits so well with the measurement that they almost completely overlap to each other. And what we see, so here from 2023, when with the same constant emission as nowadays, as anthropogenic, or also in this case, natural emissions, the CO2 concentration can only further increase by less than 10 ppm. This is my personal curve to understand these discussions of the IPCC. And here you see the green graph represents the natural emissions, including the seasonal oscillations, and this light blue graph on a magnified scale here. These both curves here belong to this scale here, and this blue graph here, this we know already from a previous discussion, with 13 ppm compared to 140 ppm increase over the industrial area gives only this 9% increase. This was the conservative way. We can even discuss this now for the other period. I won't mix too much together. Then this is reducing to less than 5%. And this gives the same good coincidence, only the effective absorption process has to be assumed to be still faster. And this was depending on the mass ratio between the troposphere and the absorption layer. So the emission rate we have here is shown also with 4.8%. This means when this stays stable from here, the future, this only gives this small further increase before the CO2 concentration in the atmosphere comes to equilibrium. Yeah, okay. Finally, you know this graph? A short supplement to historical data of Ernst Georg Beck, and we see Beck was collecting almost 100,000 historical data about chemical CO2 measurements between 1826 and 1960, at times when there was not infrared technique possible to measure as nowadays at Mauna Loa or other places, the CO2 concentration. So, thanks to Jan Erik and also Arad Indestad, they were publishing post-mortem these data from Beck and in one of our in our issues of SCC. And these calculations, I made these calculations with the same assumptions and parameters for temperature-induced emission, particularly in the tropical areas, yeah, as beforehand for the other discussion. And this reproduces here. This reproduces here with the temperature, the measured temperatures, as a combination of rural data and sea surface data represents this peak, which was found from Beck here around 1940, quite acceptable. A little bit broader, but also the later increase here can well be calculated by this data. So this is a further proof or supports this analysis. Okay, so I will come to an end. I only could answer this first question. Human emissions have almost no influence on the increasing CO2 level in the atmosphere. This already gives the answer what humans contribute to global warming. And I skip over to this second question, which would take more additional 10 minutes, but we come to the end here, to a total balance. When we look, no, this I didn't want. So why is this? Okay, I have to go. No, sorry. Okay, this doesn't work, but okay, in conclusion, I maybe I can use this here. No, I wanted to go to the final discussion, but I can't jump to this. So let me finish here at this point. We get a clear answer here already that only considering this carbon cycle and its behavior, we can understand all these different parts. Yeah, and from this point, there is no reason that we talking about the doomsday, that the world is destroying and is comes to a tipping point, or else the contribution we have additionally considered the CO2 temperature increase over the last century can be calculated by only 0.24 centigrades, not more, over the last 100 years. And when we look, on the other hand, here we have less than 10% as natural, as anthropogenic contribution to this CO2 increase. You multiply these two numbers, we come to an human-induced increase, temperature increase of about 0.02 degrees, not more. That's the result, and that's the finish. Thank you.